Okay, a short video here to talk about what I think is a really cool, interesting application of these concepts from the activity series and Voltaic cells. And it's the concept of sacrificial protection, or a sacrificial anode. So this is something that's often applied to iron. As you probably are aware of, iron is quite prone to rusting. And rusting is basically the oxidation of iron. It's the conversion of iron into iron 3 oxide, which is Fe2O3, and usually it's hydrated to some extent, so it's ionic hydrate. And this happens when iron is exposed to water and also oxygen. And so on the surface, then the iron starts to rust, but then the rust can actually travel inside of the iron structure from there, and it corrodes the iron and weakens it structurally. So it's a major problem. We use iron and steel, which is mostly iron, to build buildings and vehicles and things. So this affects a lot of different objects and structures in our world. So the idea of a sacrificial anode takes the idea of the activity series, and if you connect, so here's iron on our cell potentials, our activity series here. And if you attach a more reactive metal to the iron, then that metal will oxidize first, preferentially, instead of the iron. So the metals that are typically used are magnesium, aluminum, and zinc. Depends on the application. But if they are connected, then it is more spontaneous for magnesium to oxidize, aluminum to oxidize, or zinc to oxidize than it is for iron to oxidize. So these are these oxidation reactions. And we know they're more spontaneous because when we flip them, they get positive electrode potentials. And positive electrode potentials are spontaneous, negative delta G. So all of these are increasingly spontaneous oxidation reactions. So this is a picture of the hull of a big ship. And you probably wouldn't know this because they're underwater, but they attach giant pieces of zinc all along the hull, because sticking a giant ship made out of steel into salt water is basically a recipe for rust. It's going to just corrode apart your ship. But they regularly replace these zinc plates, and then the zinc undergoes this oxidation. And so long as there's zinc left, then all of that iron that it's touching is theoretically protected from corroding and undergoing this oxidation. So what we're trying to do here with this sacrificial protection is we're trying to prevent this process from happening. That keeps the iron intact as iron, and instead the zinc oxidized to zinc ions. Another application is with pipes underground. They'll connect pipes, and they just connect them with a wire. So they're not actually touching, but they'll connect an iron pipe or a steel pipe to a big piece of magnesium that's underground. I should say sacrificial. And as the magnesium starts to react with things in the soil, it starts to oxidize. So the magnesium is oxidizing off into Mg2 plus ions. But because it's connected by a wire, those electrons that are being pulled off of the magnesium, liberated from the magnesium, travel through the wire. They travel this direction to the surface of the iron, and so you have this electron-rich surface of iron metal, and that allows the iron to basically act as a cathode. It acts as a site of reduction. Iron can't reduce any further. There's no more reduced form of iron than just iron metal. So it causes other things, in this case oxygen, to reduce on the surface of the iron. And the equation for oxygen reducing is that it reacts with hydrogen ions in the soil and gains electrons, and it turns into water. So instead of having your iron oxidize and beginning the process of rusting, you get magnesium to oxidize instead, and the electrons travel through this external wire and turn the iron into a cathode, essentially. And because it's so electron rich, this iron, it ends up not being oxidized. It ends up being the site of some other reduction. And then other ions, basically this moist soil acts more or less like a salt bridge. And so there are additional ions in here that can sort of migrate around and keep the charge overall neutral. So it's an application. If anyone has ever seen like a lemon battery before, they do this with kids. If you take a lemon, some other sort of acidic thing, and you stick a piece of copper into it, and you stick a piece of zinc into it, and you connect it with a wire, you can make a little buzzer go, or maybe a little light come on. You'll produce a voltage. So what's happening here, this doesn't look like the Voltaic cells that I've covered. It's maybe not a traditional Voltaic cell, but it is a Voltaic cell. Inside of a lemon is acid. Acid is H+, and we've seen on our activity series that zinc is higher than H+ on the activity series. That means that when I put zinc into acid, electrons are going to spontaneously get pulled off of the zinc and cause the zinc to get oxidized. So when we stick these electrodes in, the zinc starts oxidizing. The electrons are liberated from the zinc ions, or from the zinc metal, and they travel through the external wire. They do the work. They make the buzzer go off. They light the light. And then the electrons travel down here. But again, the copper is already reduced. The copper can't reduce any further. You can't give copper more electrons to make copper minus. That just doesn't happen. So the copper is now just a surface. It's a surface for a reduction reaction. So the H pluses will be attracted to this surface with these electrons, and the H plus ions will gain electrons and will turn into hydrogen gas. So you've got your two half equations. At this electrode, we're making hydrogen gas, and at the other electrode, I've got zinc oxidizing to zinc ions. It's the same reaction that would occur if I put zinc straight into acid, but now the electrons are traveling through this external wire, and we can produce a voltage. So these kind of interesting other applications of activity series in Voltaic cell: sacrificial anode.